slide. All right, let me give my old sad song to you. Friday, I carried all the material I needed over to the Birmingham campus and I was going to try to get Blackboard updated in all my classes, or as many as I could, and then work on the rest of them over the weekend. Well, Friday, first thing I had to do was cancel 3 sections, and usually before I cancel a class, I try to call the students to tell them it's being canceled. Well, I got the first student called in the first class, and then here came the floodgate. And I had students and faculty members and everybody else coming in and dealing with me for the rest of the time I was there. And then we had a meeting at 12:30, and and I was late to that because I was dealing with a student somewhere else. So I got 0 done on Blackboard on Friday at class. So I carried it home with me, all the stuff home with me, and I got some work done yesterday. We were out of town part of the weekend, and I couldn't get anything done. But last evening when I got home, I started working on stuff and made pretty good progress until I went to load stuff on Blackboard. It would not load at all. And another student, and one of the students in my first class said he couldn't get on Blackboard last night either. Either it went down, or they were doing maintenance on it, or something, but I could not access Blackboard. So I'm counting on, after class today, from 3:15 to 5:15 to get as much of that done as I can. But of course, I'll go down to my office and about 15 people will be waiting on me, and I may not get it done either. But I'll try to get it done then. So if you've been looking for things to be on Blackboard, they're not there yet. But I won't be able to get all 7 classes done in the 2 hours I got, but I'll get started on them and get as much as I can done. I got several corrections made, so I'm ready to do it, but not for every class. So, anyway, Treddy's here, and you don't have the class book. Now, in our calculus book, there is a chapter on differential equations. Does yours have one? It's probably just a very great. I don't know why our book does that, so yours doesn't, which makes sense. Why have a chapter on differential equations when there's a whole course in differential equations? So you can either get the text, and by the way, if you find anyone who had it last time, do you have this one or the previous? You have the previous. Do you have this? You don't have the text yet. But you can sometimes get them online. You can rent them. You can do a variety of things. It's not a huge book. Did you remember how much it cost in the bookstore? What's that? I know, but did you check in the bookstore?
107 used, and new is like 143.
Okay. Say that again.
Used is $107, and
brand new $7.
Yeah, $107.
Oh.
And then brand new is $143.
Wow, that's not much difference. I thought you said 170 and 143. I said, buy the new one, because I thought it was cheaper, but no, okay, I got you. Okay. All right, but we've, when you get to YouTube, you'll see the syllabus there, you'll see research paper instructions. You have to do one for each class. My locator card, that's updated and out there on both things. I just don't have it on Blackboard yet. And I will have on Blackboard some of the websites that either students have told me about or I found that I thought might be helpful to you, YouTube videos, that kind of things. And then I don't have it there yet, but I will have the link to get straight from Blackboard to this class's playlist on YouTube. And by the way, what you'll see there are a lot of sections we haven't done. They're from previous times I've taught the course, so you can go and look at what's ahead if you want to, or listen to what's ahead. But if you'll get, and by the way YouTube does it in the playlist, they put the ones you put in first at the top and the most recent at the bottom. So go to the bottom and you'll get the playlist, and you'll see the ones I put in this term. The others will be at the top of the list if you find it. Once I give the link to you. All right, we're in Chapter 1, Section 1.1. We had done 4A. Is this where you got it? And ready to do 4B? Is that right? Okay. So here is 4A, page 6. Okay? So we didn't get very far in this course. Okay. Here's some equations. Let me get my pen activated. Okay. 1 minus y times y prime plus 2y is equal to 3 to the x. I'm sorry, it's e to the x. Sorry, I can't read. Okay. That's a differential equation, right? Here's a derivative in it. Is that an ordinary differential equation? Yes, the prime notation indicates ordinary. Okay? Is it a, what order differential equation is it? Say again? First order, because it's dy dx. First derivative is the maximum derivative. Is it a linear differential equation? No, because you have a y times a y prime that keeps it from being linear. Now, you might ask yourself, can I divide all three terms on both sides of the equation by 1 minus y, and then you'll have a y prime by itself. That will be linear. But then you'll have, in the second equation, second term here, you'll have plus 2 over y minus 1. Okay? Well, when you have a 2 over y, that's not a linear term in y. So, no, there's no way you can make that linear in y. Okay? So, it's the ordinary differential equation. It's the first order differential equation, but it's not a linear differential equation. Okay? How about this one? d2y dx squared plus sine y is equal to 0. Ordinary differential equation? Yes, it's not partials. If it's partial differential, that would not be ordinary. This is an ordinary differential equation. What order? Second order. Is it linear? Sine is not a linear function of y. If that would have been a sine x, yes, that would have been linear. X could be anything you want to. Move it to the other side of the equation, and you have d2y dx squared is equal to minus sine x. That would have been perfectly fine linear differential equation. This is not linear because the y is not a linear form of y. And this is okay, that's linear. You just have second order, second derivative, but it's just to the first power, you might say. The sine is not to a linear, it's not a linear function of y. Okay, here's a third one. d4y dx to the fourth plus y squared is equal to 0. Ordinary or partial? Ordinary. What order? Second, fourth order. Very good. Linear or nonlinear? Nonlinear because of y is y squared. Okay? So you can't multiply a derivative of y by a function of y, or even have a y double prime times a y prime. You can't do that either. That won't be linear. It can be, a differential equation, but it just won't be linear. And you can, if you have a function of y by itself, it has to be a linear function of y. Y squared is not linear, sine y is not linear. e to the y is not linear. Log y is not linear. 1 over y is not linear. It would have to be just some function of x times y by itself. Okay, so those are nonlinear forms. Okay, now definition here. What do we mean by solution of a differential equation? Okay, and stated back on page 2, one of the goals in the course is to solve or find solutions of differential equations. So here's a definition. Since some of you don't have books, I will write this out. My writing stinks and I abbreviate like crazy. Okay, so stand by. Any function phi, okay, defined on some interval I, okay, and possessing at least n derivatives that are continuous on I. The function possessing at least, I think is how it's phrased, n derivatives that are continuous on I. Continuous on that same interval I, which, when substituted into the nth order ordinary differential equation, DE stands, what is wrong with this thing? DE, differential equation, that's what that stands for, reduces the equation to an identity. I didn't spell it right, identity. Is said to be a solution of the differential equation. A solution of the equation on the interval. On that interval. Okay. Now, in other words, a solution of an nth order ordinary differential equation, as indicated back on page 5 at the top of the page, capital F of x, y, y prime, y double prime up to y, the nth derivative of y is equal to 0. Okay, so here's what we're going to call it. F as a function of x, that's the independent variable, and then your y would be phi of x, y prime would be phi prime of x, I can't write, okay, phi double prime would be your second derivative with respect to x, dot, 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 up to and including the nth derivative of phi. And by the way, when you put the n in parentheses, that's how many derivatives it is. And not in parentheses, that's a power. And in parentheses is a derivative. That number, the nth derivative of phi as a function of x, this is equal to 0. Now, sorry about this. I slash my zeros, and of course I slash phis. So in this case, I'll leave the slash off the 0 if I can get the eraser to work. Okay, most of the time I slash zeros, but when I got phi in the equation, I'll try not to slash it. Okay, and that's true for all x's. Why is it not writing? For all x on the interval I. Okay. Now, let's talk a little bit about what that interval is. That interval of definition, you cannot think of the solution of ordinary differential equation without simultaneously, at least mentally, saying, where is this a solution? Okay? I did one of my calculus classes I had earlier today, I think it was Cal 2. Cal 2. This morning. We had, we're talking about the integral of 1 over x. But if you think about the graph of 1 over x, it's here in the third quadrant, and it's up here in the first quadrant. Okay? So, you cannot talk about an interval going from -3 plus 2, because that involves a discontinuity, an infinite discontinuity. You can't bridge that. You cannot talk about that. You can talk about the integral of it as long as the interval is completely over here for negative x's, or completely over here for positive x's, but can't have on one end a negative x, on the other a positive x, because you have an infinite discontinuity between the two that you cannot get rid of. Okay? So, that's what it means. When you're talking about a solution for a differential equation, you have to also think about, where are we defining this? Is this for all real values x's? Sometimes they are. Sometimes they're not. Okay? For instance, if you had a 1 over x minus 1, or something, or y minus 1, or something like that, obviously x couldn't be 1 or y couldn't be 1, because you can't ever divide by 0. So you have to exclude those places where you have discontinuities. The interval I in those definitions is variously called the interval of definition, interval of existence, the interval of validity, or the domain of the solution. All those work. Can be an open interval from A to B, closed interval A to B, including A and B, or an infinite interval A to positive infinity, negative infinity to B, or even negative infinity to positive infinity. It can be any of those. So, let's move to example 5. By the way, this text does not have PowerPoint, so I have to write everything down. That's why poor thing is going to be really sloppy. Okay, so let's do example 5. Verify that, but these will all be recorded and out there on YouTube ultimately. Probably be the end of the day today before they get there, but they'll be there. Verify that the indicated function is a solution for the given differential equation on the interval negative infinity to positive infinity. So this is for all real numbers. So here's your differential equation. dy dx is equal to x y to the 1/2. Now, unfortunately here, they're not telling you how they got it. They're just saying, here's a function, see if it's a solution or not. Okay? Here's the function, y is equal to 1/16 x/4. How are you going to verify whether or not that's a solution? Say again? You take a derivative. Always a good answer. So I can, and I hope you don't get offended by this, but in children's church, when the leader asks some question and the kids don't have any idea what they talked about, one of them say Jesus, and that's always a good answer in church. They can't say, no, that's a bad answer. They always say that. Okay. So when you're dealing with differential equations, never a bad idea to take a derivative. Okay, let's do it. dy dx is equal to what? There's your y. dy dx is? There's your y. What's dy dx? 1/6 1/4 x to the third. All right? Okay? Now let's plug that in here. 1/4, that's dy dx, 1/4 x to the third is equal to, this is a question mark, we don't know if it is or not. Is that equal to x times y to the 1/2? Well, let's see what y to the 1/2 is. If that's y, what's y to the 1/2? This is y. What's y to the 1/2? Square root of y. Say again? The square root of that. That'd be what? 1/4 x squared, right? Square root of 1/16 is 1/4. Square root of x to the 4th is x squared, right? Okay? So that'd be x times 1/4 x squared. Are those two equal? Sure enough, 1/4 x cubed is equal to 1/4 x cubed. You get an identity? Good. That right here is a solution to this, because when you do the operations that are indicated here, you get an identity. Right?
Could you have gone the other way and tried to take the integral?
Kind of. Okay. It's an excellent question, and I wish this is how they would have presented it. Here's what you do. It really is taking an integral. This is one that you can solve by what they call separation of variables. We haven't gotten there yet, but since you ask, I'm going to answer. Okay. Okay. Now we write this in differential form. This is in derivative form. In differential form, this would be dy is equal to xy to the 1/2 dx, right? But I want all the y's together and all the x's together, so that you can do that on this one, so we're going to separate. So we'll divide both sides by y to the 1/2. Okay, and these go away, and what we have, take an integral of both sides of this, the integral of, I'm going to write that slightly differently if this is okay with you. How do you write 1 over y to the 1/2? How do you write that in exponential?
1 over y to the 1/2?
Yeah. Right. Y to the, second? Negative 1/2. Got it. dy is equal to x dx. Right? So, and we're going to integrate that side too. Okay? Now, what's the integral of y to the minus 1/2 dy? Y to the 1/2 times 2, right? Divided by 1/2, which is times 2, is equal to, and what's the integral of x dx? X squared. X squared over 2. Okay? All right. Now let's solve that for y. So this will be, let's first divide by 2. So this will be y to the 1/2 is equal to 1/4 x squared. And square both sides, right? Right? By is equal to 1/16 x to the 4th. That's one way to get it. Now, that's not completely an answer. You just don't need a plus c in there. Anytime you do an indefinite integral, which both of those are, you need a plus c. So in one or the other of those, you probably need a plus c in there. But I didn't want to put that until I got the final thing for y. So now I put a plus c. They just said a solution, not any old solution, not all the solutions. So that certainly is a solution. So is that what you're asking? Yeah. That's how you would do it if you were separating variables and going from there. This book takes you through all this, and a lot of math books do this now, and physics and other books do. You start looking at some sort of abstract things. Hey, see if this will work, and stuff, and they don't tell you how you got the answer. I just assume let's go on. Well, here's how you solve it and do it, rather than, see, this will be a solution. Verify that for me,
Not
Yeah.
to hold you up or anything, but I understand how you did the second part.
Right.
How did you get the first way you did it? What?
Okay, all we were doing was verifying to see if this was a solution for here.
Yes.
So what I did, this had a dy dx, so if this is a solution, then the derivative of that solution would be this. That's what's going to go on this side. Over here you had x times y to the 1/2. Well, I got to take the square root of y to get this term. So the square root of this y is the square root of 1/16, which is 1/4, times the square root of x squared, x to the 4th, which is x squared. So that gives you that. So then I put this, which is this thing,
Oh, okay.
is equal to x times this thing, and then see if they are equal. And this is a question mark here, and sure enough they are. Check mark. Okay.
I'll just it's something that's not.
Yeah. Okay. Let's do the B for that. It's again a ooh-wah. Yeah, it works. But let's see if we can make it make sense. Here we have a y double prime minus 2y prime plus y is equal to 0. There's a differential equation, ordinary differential equation, second order ordinary differential equation, second order linear ordinary differential equation. Okay. Here's what they suggest a solution is. Y is equal to x e to the x. Now that's not all your solutions, that is a solution. Well, what are we going to need to do to verify it? Take a derivative, you got it. Y prime is equal to? Good old product rule, right? How does that go?
Hold on. If we take the derivative of the y equals x to the e, raised to the x.
Okay, no. Y is equal to x e to the x.
Okay, yeah.
Now I want to take a derivative of that.
Okay.
That's a product of two functions of x. So how do you take the derivative of a product? Okay, which is? Okay. Okay, so that'd be e to the x plus x times e to the x. All right, there's your derivative. First times the derivative of the first times the second plus the second times the derivative of the first, or however you want to say that. Yeah. But we also need a y double prime, so let's go on and do that one. And what would that give you? E to the x plus e to the x plus x e to the x, which you could combine like terms and get 2e to the x plus x e to the x. It's an ugly x, isn't it? Okay? Now we take this and plug it back here. 2e to the x plus x e to the x, right? Minus 2 times e to the x plus x e to the x plus x e to the x, that's your y. Is that equal to 0? Right? This is 2e to the x plus x e to the x minus two e to the x minus 2x e to the x plus x e to the x. Is that equal to 0? Well, let's see. 2e to the x minus 2e to the x, that's 0. Okay? And here we have a minus 2x e to the x plus 2x e to the x, and that's equal to 0. Yes, indeedy, that is an identity. Right? So yes, there is a solution. Not the only solution, but a solution for that differential equation. Okay? See how to do it? Now, I'm going to find another solution for that. Y is equal to 0. Would you say that's the solution? Y is equal to 0. Y prime is equal to 0. Y double prime is equal to 0. And 0 minus 2 times 0 plus 0 is 0. Okay? That's called the trivial solution. Anytime you have, and there's going to be two things we call homogeneous forms. When you have the right-hand side equal to 0, we call that a homogeneous or differential equation. Later we'll say something else is homogeneous. You got to keep them separate. This is, anytime you have a homogeneous, then y is equal to 0 is a trivial solution. It's always going to work. Okay? That means you have an infinite number of solutions because, well, not necessarily. That could be the only differential equation, the only one that works. For instance, if that had been a minus 3y prime, that would be the only solution. The only solution. Okay? This one will work. And certainly, it will work if it doesn't even fit in that family. Okay? But it is a solution. Y is equal to 0. And it's called a trivial solution. Okay. Now, they have also the graph of a solution phi of an ordinary differential equation is called a solution curve. And you can have one curve or an infinite number of curves, okay, depending on how many solutions you have. And what's that?
Can you just take the antiderivative of y prime to the second first y prime?
Say that again.
Can you take the antiderivative of them?
One more time. Can you take?
I'm not good at explaining stuff. I'm not good at really explaining stuff. Like,
What was the question? I just can't hear. My hearing's bad.
oh, I was just saying that, like, see this right here?
Yeah.
Can we, like, I don't know, like, take the antiderivative of this and this too?
Ooh. I don't know how to type the antiderivative of the second derivative. That's a little bit harder to do.
Yeah, that's probably it.
Yeah.
I don't know. I was just.
Now, I thought what you were asking at first, and I thought, great insight, okay. I thought you said take the x out of your y there. Guess what? Y is equal to e to the x would also be a solution to this. I was surprised you saw it. But if you put y is equal to e to the x, y prime would be equal to e to the x. Y double prime would be e to the x. And you have e to the x minus 2e to the x plus e to the x. That's equal to 0. I thought that's what you were asking. I thought, wow, pretty sharp. Yeah. But that wasn't what you were asking. I thought you were. Yeah, I was hoping you were. Okay, that is another solution. And by the way, the linear combination of this one and another one, which we haven't even talked about what that is yet, that gives you the total solution for that differential equation. You write some linear combination of that, and that's all your solutions. Okay. So let's go to example 6. That's going to ask us to do something else. Oops, hit the wrong key. What is the domain of this function? Y is equal to 1 over x. What is the domain of that function? X is not equal to 0.
Oh, yeah, not.
Yeah, any value x in the world as long as x is equal to 0. another way of expressing it from x equals minus infinity all the way to x equals 0, but not counting x equals 0, and then starting at x equals 0, but not counting it, going all the way to x equals positive infinity. So 0 to x, open, x to 0 to positive infinity. That would be your domain of that. You just can't have x equals 0. Okay? So there's your domain of that. The domain of that considered simply as a function set of all real numbers except x equals 0. So when we graph that, if we were to graph, and I waved my arms before, basically it looks something like this, right? Where this is 1, 1, this is minus 1, minus 1. And then they get closer to 0 going this way, closer to 0 there. Yeah. That's what that function looks like. Okay? Now, this function could be, if this was a differential equation, it's just talking about that. In other words, if you had a domain that was anywhere over here, anywhere as long as it did not include 0, you're fine. This is what I was saying before. Also, on this side, any value can't be x equals 0, x equals 0.1 to infinity. That would be perfectly fine. 1 to 7, 0.03 to 0.05. That would be fine. If you have an interval anywhere, as long as it doesn't contain the number 0. It can't be negative 1 to 1. Could not happen then, because the function is not defined at 0. So you can't integrate over that. You can't do anything there. Okay. If, however, you just had 1/2 of that, not this one, only that one, yeah. Anywhere in that domain, you could talk about having a solution for a differential equation which contained that, okay? Or whose solution was 1 over x. All right. Another sort of definition for us, top of page 8, or somewhere thereabout, depending on what book you have, okay? Explicit and implicit solutions. Okay? A solution in which the dependent variables, usually y or whatever, phi or whatever, is expressed solely in terms of the independent variable and constants. Okay? That's said to be an explicit solution. So if you have y is equal to some function phi of x, that's usually an implicit solution. You can isolate the y, and you can have any combinations of x's over there you want to. You can have numbers in there, you could have functions, you could have e's and logs and sines and tangents, or whatever you want over there, as long as you can write y as some function of x and x alone, that's an explicit solution. Okay? In the last two examples we had y is equal to 1/16 x to the 4th. That's an explicit solution, okay? Y is equal to x e to the x. That's an explicit solution. Any combination of those. Y is equal to 1 over x. That's an explicit solution as long as x cannot equal 0, okay? All those are explicit solutions. Okay, and we had the equations for them too. I didn't do the third one, but its equation would be, how did I miss that? Where is the differential equation? there it is. Okay. Here they wanted you to verify this too. Here's the differential equation. Xy prime plus y is equal to 0. Okay? That's a linear first order differential equation, ordinary differential equation. Okay? And they suggest to you that y is equal to 1 over x as long as x is not equal to 0. Okay? They suggest that is a solution for that differential equation. Let's see if it is. What are you going to have to do first? First, I would rewrite this as x to the minus 1. Now I would take a derivative. I'd much rather take a derivative of a power than I would of a fraction. Okay? You agree? Wow, okay. So what is y prime? It's what? Negative 1. You got it. Or you could write that as 1 over x squared, or minus 1 over x squared, right? Yeah. Okay. So let's write it that way. Is x times a negative 1 over x squared, that's your y prime, plus your y is 1 over x, is that equal to 0? Well, let's see. Yeah, that would be negative 1 over x plus 1 over x equals 0. Yes, that would be true. As long as x is not equal to 0. Okay, it can't be equal to 0 anywhere. In other words, the domain would have to be all negative values x or positive values x. So that could go from here are some of the possible domains. Minus 3 to minus 1. That would certainly work, wouldn't it? 1/2 to 10. Now, these are not ordered pairs, these are open intervals. They look like ordered pairs, they're not. How about this one? Minus infinity to 0. If that had been a bracket at the end, not. See, an open parentheses, that means you don't include the endpoint. A bracket would mean you do include the endpoint. You cannot include 0. So that would be perfectly fine. Another one. 0 to infinity. Again, as long as that's a parentheses, that's fine. If that were a bracket, no, it's not fine. Okay. You cannot include 0 in there. Okay. All those, and there's infinite number of intervals you could do. Okay. So those are all explicit solutions to differential equations. All right, it says, moreover, the trivial solution is an explicit solution of all 3 equations. We have 4, by the way, folks, not all 3. The first one we had, no, I'm sorry. I disagree with it, the hair. It said, moreover, the trivial solution y is equal to 0 is an explicit solution of all 3 equations. I don't believe so. Y is equal to 0 cannot be a solution of this one, can it? Oh, yeah, it can. The equation itself, it can. X can't be 0, but y could be 0. Because y, if y is equal to 0, y prime is equal to 0, 0 plus 0 is 0. Yeah. Y is equal to 0 is a solution. The reason I had doubts there, I thought y can never equal 0 is this. But you see, this is not, this is a different solution than y is equal to 0. Okay. All right. it says here, this is sort of a broad statement, when we get down to the business of actually solving some ordinary differential equations, which we've only done one when you asked me to, you will see that the methods of solution do not always lead directly to an explicit solution y is equal to phi of x. This is particularly true when we attempt to solve nonlinear first-order differential equations. Often we have to be content with a relationship that's something like this. G of xy is equal to 0. Okay? That defines a solution of phi implicitly, not explicitly. So here's the way we summarize that definition in your text. A relation G is a function of x and y equal to 0 is said to be an implicit solution okay, of an ordinary differential equation, ODE, ordinary differential equation, that's my abbreviations here, on an interval I, provided that, okay, I thought one of you was asking a question. Provided that there exists at least one function okay, at least one function phi that satisfies the relation as well as the differential equation. Okay, on I. Okay, on the interval I. Now, that's all we're going to say about it, but we'll run into it. And you've done it sort of already back in calculus class. When you had an equation that you could not isolate the y, say it was x times y is equal plus sine y is equal to something 0. There's no way you can get those y's together and the x's separate. So all you can hope for is have an implicit solution then, that you have x and y's intermingled and they come out working. Okay? So they have remarks at the end of every section, or at least on the end of every section. And sometimes those go a little bit deeper. So let's do example 7. Here's a relation. X squared plus y squared is equal to 25. Okay? By the way, what does that describe for you?
Looks like a x squared plus y squared equals r squared, something like that.
A what?
What's it called?
Circle
Yeah.
of
Circle of
what radius?
5.
Yeah. See? X squared plus y squared is equal to 25. So it's centered at the origin. Okay? That's your standard solution for that. Okay? Or equation for that. Okay? It says show that that's an implicit solution for this differential equation. Okay? So here's the differential equation. Before they gave the differential equation first and then gave you this. Dy dx is equal to minus x over y. Okay? Now, in In order to do that, you have to come up with dy dx, don't you? How do you do that in that equation in that form? Okay. In other words, move the x squared to the other side. Is that what you said? Okay. And you'll have y squared is equal to 25 minus x squared. Is that your first step? Is that what you mean? Huh? No, that would be logical. And then you take the square root of both sides, right? And that would give you y is equal to plus or minus the square root of 25 minus x squared. Oh, yeah. Now you have two possibilities for any one value of x. You have two possibilities for y, so it wouldn't actually be a function. It would be a relation. That's why they call it a relation. You can do it that way. This one you can. There's a little bit simpler way, I think, anyway. And what do you say in Sunday school class? Take a derivative. Oh, no, this is a different calculus class. Okay. Yeah. So take a derivative. It's almost like Sunday school, isn't it? All right. You take the derivative of this, what do you get? 2x plus 2y, y prime equal 0. Okay? Remember, y is a function of x, so you take a derivative of x, no problem. X squared, no problem. When you take the derivative of that, it's a chain rule issue. 2y times derivative of y, which is dy dx. Now you can solve that explicitly, right? By subtracting 2x from both sides. And you have 2y, y prime is equal to, I'm going to write that, dy dx. Okay, that's the same as y prime. Is equal to minus 2x, right? Now divide both sides by 2y. These go out here, and here your 2's go out, and what do you have? dy dx is equal to minus x over y, which is exactly what you have there. Okay? Now, you kind of could have done that Emmanuel's way too, but you'd have to first do it for one set of x's and then do it for another set and stuff. This way pretty much takes care of it all at one thing. You don't have to set up two different conditions and go by either or both or whatever. Okay? Now, by the way though, this is only good on the open intervals minus 5 to 5. So x is in minus 5 to 5. All right. Why is that true? Frankly, it looks like it should be closed interval minus 5 to 5. Because x could go, if x were minus 5 squared plus y squared would be equal to 25. What's minus 5 squared? 25. So 25 plus y squared is equal to 25. Obviously, y is equal to 0. No choice, right? Okay. Well, could you do 6? 36 plus y squared is equal to 25. Why not? 36 is always positive. I'm sorry, y squared is always positive. Can't think of a positive number you can add to 36 to get 25. It would have to be a negative number. But y squared is never negative in the real number system. Okay? So therefore, yeah, you have to stay between minus 5 and 5. And 0 works fine for x. Y is equal to plus or minus 5. Okay. So there is basically an implicit domain here. Now, doing it the way Emmanuel was sort of suggesting, if you had solved that for y, okay, you come up with two solutions. By the way, like we said, this is a circle of radius 5. If you try to solve it for y, you're going to get one of two solutions. That half circle or that half circle. But to get an equation, it can't be both, because that's not an equation, that's a relation, okay? And then you have to come up with a solution for both of those, and you get one positive, one negative, but then it's just a lot messier to do. Okay. Now, the next sort of thing we're going to talk about are families of solutions. Okay. We go to, still trying to get my thing right. Go 2 to 3:15, right? Okay, so we got about 10 more minutes. All right. Most of my other classes are 4-hour classes. I'm used to those, but going back to 3, which is the most common, I had to stop and think about it. Families of solution. In study of differential equations similar to that of integral calculus, you usually don't get a single solution, especially for when you're integrating an indefinite integral. Remember what you always had to put at the end? Plus c. And for whatever value of c, you could have equation here, 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 and here. All those derivatives are the same for all those, but you can add a c to it and have a completely different solution. Well, for differential equations, it's not quite that obvious, but you have families of solutions that make all the things work. Now, you can have a one-parameter family of equations. You can have an n-parameter family of equations, but occasionally you'll have just some solution that just happens to be a solution not related to any others. That's called, by the way, a particular solution. Okay? Those parameters generally are somewhat arbitrary unless you know something specific about the problem. Okay? Let's just go back to this one. And what if you had x squared plus y squared is equal to c? That might be a parameter. Well, that would be a family of circles. And c is equal to 0. You just have a single point. We might want to exclude that one. C is equal to 1 would be a circle of radius 1. C is equal to 4 would be a circle of radius 2. 9, and so on. So you have a family of circles. Okay? Now, could C ever be negative? No, because a positive number plus a positive number can never be a negative number. Okay? In fact, I think that's why you would have to say C is not equal to 0 either. Because that would be really a trivial solution. X equals 0, y is equal to 0. That would be the only possibility to have C is equal to 0. Okay? So that would be a single family system of solutions. Single variable, single parameter system of solutions. Okay? Family of solutions. But the particular solution might be 0, 0, because that might be a particular one because, you don't multiply or do anything else with that. So the parameters in a family of solutions, okay, I want to just, I don't want to draw these, so I want to just show them to you. I know that Emmanuel has a book already. But this would be a graph of a family of solutions. The green one is when C is less than 0. The blue one here is when C is equal to 0. The red one here is when C is greater than 0. And you can have a whole bunch of others, everything in between. Okay. Obviously, the yellow one is C between the blue and the green, so it would also be less than 0, but not as small as the green one would be. Okay. Sometimes they look like that, very regular, somewhat of a pattern. Other times they're not nearly as pretty. Okay. For instance, this one, some of these are going up and then down, some of them are going down and then up. Okay? And it's sort of hard to see what the relationship is there. So let's take a look at a few of those. Let's see what we can do in 5 minutes. I think we'll need to clear this. For all real numbers, values of C, the Ron parameter family, y is equal to cx minus x cosine x is an explicit solution of this linear differential equation. xy prime minus y is equal to x squared sine x. Okay? They say verify it. How would you go about verifying that? Take a derivative. Very good. Okay? Y prime is equal to? With respect to x, right? Through cx.
It's just C squared.
Derivative, not integral.
Oh, it's just C.
C. Okay, that means yes in Spanish. C. Okay, yeah, that's it. Okay. C minus. Okay. Okay, wait. If you're taking derivative of the first, leave the second alone. Cosine x plus you want that to be a plus or minus? I thought you said plus. Huh? All right. I say it's a positive too. Okay, I thought you then told me negative. Okay. Plus x times. Okay, it's really a minus sign, so that made the minus become a plus. Yeah. X times sine x. You got it. Okay. Now let's plug it in and see what we get. X times c minus cosine x plus x sine x minus y, which is cx minus x cosine x. Is that equal to x squared sine x? Let's see what we get. Here we get, when you distribute inside here, you get xc minus x cosine x plus x squared sine x minus cx, minus of minuses, plus x cosine x. Is that equal to x squared sine x? Well, let's see. Here's a XC and a minus CX, they add to 0. Minus X cosine X, a plus X cosine X, those add to 0. And sure enough, X squared sine X is equal to X squared sine X. Yes, that is a solution. And that's what we call a one-parameter solution because you only have one parameter, and it's C. Yes, okay? Now, and that should be good for all real values C. I'm sorry, X, because X cosine X is differentiable everywhere. No sweat. Sine and cosine, differentiable everywhere. Okay. That's the one. This is your family of solutions. When C is equal to 0, you just have X cosine X, and that's that blue curve there, and that's basically how it looks. But when C is anything other, like positive, then you have like a line that is a greater curve if you went peak to peak, say. Or if C is negative, it flops it over to the, it goes negative first, not positive first, okay? So, sure enough, that's your family of solutions. I can't look at them and tell what they are. You have to generally use a graphing package to do it for you. Okay, and I'm afraid that means we'll out of time, so we'll start with 8B next time. So homework exercises here, and by the way, we didn't quite finish this section, did we? Okay. I think you can do any of the odds 1 through 7. I think you can do 9. I think you can do either 11 or 13 or both. I think you can do either 15 or 17 or both. And I think you can probably do 19. And you can start looking at 21 and or 23. All right, I think that'll probably be enough. We'll pick up the rest of those next time. Okay, any questions? By the way, the odd number answers for most of the exercises are in the back. If there's some that are not in the back, I usually won't give them to you as a possibility.
You want me to pick up the cover?
Sure. Want the back cover that has the ISBN on it?
Yes,
both of them?
that'll work.
Okay. Be sure you get the student edition, not the instructor edition.
Okay.
They're not supposed to sell the instructor edition. Okay. I don't think it really matters. I think they have all the same answers in the back, I believe. Yeah. You got enough light? Okay.
Yeah, I got enough. I was just gonna make sure I got the title and everything.
All right. We'll see you Wednesday. I'll go and shut this baby down.